So in this video we're going to talk about quadratic functions and models, and we're going to start with something that should be review, solving quadratic equations and inequalities. So let's take a look at the example here. So the first example, we want to solve for x. We have this equation x squared plus 4x plus 1 is equal to 0. Remember, there are actually three ways to solve a quadratic equation. 1, you could factor it. 2, you could complete the square. Or 3, you could use the quadratic formula. In this case, if you try to factor it, you see that you can't. But let's try. So you say x plus or minus something times x plus or minus something is equal to 0. And of course, the somethings would have to be 1 because there are only two multiples or two factors of 1, which are 1 and 1. But you can never add or subtract 1s and turn it into the number 4. So you can't really factor this nicely. So the second way to do it would be to complete the square. So let's complete the square on this thing. And so let's start here with this equation, quadratic equation, x squared plus 4x plus 1 equal to 0. And remember, to complete the square, you just follow the saying. So what's the saying? We add half the middle term squared. Alright, so what's the middle term in this case? So if we go back and we look, you'll see the middle term is 4. And so we're going to take half of 4 and square it. So we have x squared plus 4x. And then half the middle term is 2. And if you square it, you get 4 back. And we'll take away it right next to it. And then we have the plus 1 equals 0. Remember, you add and subtract the same number, and it really doesn't change the equation at all, because if you add 4 and take away 4, you really added nothing to the equation. But what you do get, so what we do get is that this piece right here can be written as a complete square. So we should be able to write this as x plus or minus something. It's plus in this case because you have a plus there. And then 2, because 2 squared is 4, quantity squared. So if you multiply this out, or if you want FOIL it out, you'll see you get back x squared plus 4x plus 4. And then of course we have the minus 4 plus 1, which is actually minus 3. So we have the minus 4 plus 1 there, which is minus 3, and this is still equal to 0. So what happens when you complete the square is now you can solve actually for x. So you can add 3 to both sides. And so on the right hand side you have something squared, so x plus 2. Quantity squared equal to the number 3. We can undo the square by taking the square root of both sides, so x plus 2 is equal to, and remember it's plus or minus on the right hand side, plus or minus the square root of 3. And so then finally we subtract 2 from both sides and we get our answer, x equal to negative 2 plus or minus root 3. And so here's our answer for part A. Now you could have also used the quadratic formula. So remember, the quadratic formula says x would be equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. But you'll get exactly the same thing. In fact, in the activity we did, we saw that this actually comes from completing the square of the equation ax squared plus bx plus c is equal to 0. Alright, let's talk about how we solve quadratic inequalities, because this is a little bit different. So here's our inequality right here. Here's our inequality, 2x squared minus x minus 21 is less than 0. So to solve this inequality, we can't solve directly for x. So what we're going to do, the idea is you can actually factor this thing. We can figure out when this thing is equal to 0, and then we'll figure out when this thing is actually positive or negative. So let's factor it. So it's actually not too hard to factor. It has to be equal to 2x plus or minus some number times x plus or minus some number, if we can factor it. We want this to be less than 0. And so here, the 21 tells us it's probably 7 and 3. But it matters where you put the 7 and where you put the 3. So if we put the 7 here, and the 3 here, I think that'll actually do it. So it'll do it because we need to get a -1. This minus sign right here is really -1. And so if we put a minus here, that'll be -7x. We have -7x's here. And then if we put a +3 here, we have 3 times 2, which is 6x's. And so take away 7x's, add 6x's, you still lost an x. So here's a factorization. Let's set it equal to 0. And so when we set it equal to 0, we're basically trying to answer the question, when is this expression equal to 0? Not when it's less than 0, but when it's equal to 0. And so x plus 3 is equal to 0. And you get 2 answers, of course, because you're multiplying. This times that is 0, so either this is 0 or that is 0. And so you solve this one, we add 7 to both sides. We get 2x equal to 7. And then divide out by 2, and so x is equal to 7/2. Or we could have, over here, subtract 3 from both sides. We get x equal to -3. Now these are not our answers, even though I'm going to put a circle around them. None are my answers, but they're where this expression here is going to be equal to 0. They're not answers because if you plug it in, 0 is not less than 0. Remember, this is a less than sign, because if you turn it a little bit, it looks like an L. So you can see that's less than. It's nice, easy to remember which one's less than. And the other one, of course, this sign is greater than because it doesn't look like an L. Alright, so what are we going to do with this? So once you find the zeros of this equation, what we can do is we can make a sign diagram. So let's make a sign diagram right here. And so a sign diagram, the idea is we can plot these 2 points, so -3 and 7/2. And we just want to figure out, when is this expression right here positive or negative? So we know when it's 0. It's 0 at these points here, -3 and 7/2. And we can even use the factored form if we want to. Sorry. So we can even use a factor form if we want to. So let's do that here. So that the factored form is 2x minus 7 times x plus 3. And we're just going to plug in values here. We want to plug in values to the left, in between, and to the right. So a value to the left would be like, let's plug in -4. And a value in between, nice easy one, would be 0. And a value to the right, 7/2, I think is 3.5, so probably positive 4. And so if you plug -4 into this thing, you're going to get -8 minus 7 times, you plug -4 here, it's going to be -1. And now that's a negative times a negative, so this will be a positive. So that's important. So that's what that's saying. Let's use green too. So it's positive. It's a good thing. It's positive. What that means is that all the numbers, basically all the input values from here to here, up to -3, will give you a positive output value. Whereas if you plug in 0, what happens? So if we plug in 0 here, we get out -7 times positive 3. And so that's going to be negative. And so that means all the values in between -3 and 7/2 are going to be negative. They're going to be less than 0. And then if we plug in 4 into our expression, 2x minus 7 times x plus 3, what happens is you get 8 minus 7, which is a 1. And then plug in 4 here, 4 plus 3 is 7. And so it's positive. And so all the values to the right, 7/2, if you plug it into this expression, you get a positive number. Now what we want is what? We want to know when it's less than 0. So when it's less than 0, we care about this red stuff right here, and because it's less than, we don't include those endpoints. We just take all those values there. So our answer would be between -3 and 7/2. So if you give me a number between -3 and 7/2, and you plug it into this expression right here above, this 2x squared minus x minus 21, it should be less than 0. So when you solve an inequality, you often get an interval solution, whereas when you solve an equality, you typically get a sort of discrete solution, meaning just a finite number or not an interval, right? Not a continuous number of things. Okay, let's move on. Let's move on to today's question. So today's question, we really want to focus on what are called quadratic functions. So what is a quadratic function? And so to try to motivate the answer to this question, let's take a look at this table and try to find the missing value. And if you look at this long enough, I think you could probably guess at what that value might be. And so on the left-hand side, here are our input values, and you see that they're changing by 1, whereas our output values are not just changing by 1. This one goes from 1 to 2, which does change by 1, but 2 to 5 changes by 3, 5 to 10 by 5, 10 to 17 by 7. So what do you think this next one would be? And you can kind of see the answer already. I mean, this changed by 1, so you basically add 1. This one changed by 3, so you added 3 to get to the next one. Here, 5, and then here, 7. Then we could guess that probably here would be the number 9. So if you add 9 to 17, I think you get 26, and so on. So what's happening here is that each time, it's not changing by the same number, right, but it's changing by a set of numbers that definitely has a pattern. And what's that pattern? Well, if you think of the difference between these numbers here, you'll see that they're all the same. They all differ by 2. And so what happens is, if we think about what a quadratic function really is, a quadratic function is something that has what's called linear rate of change. Now remember, when we talked about linear functions, right, so when we talked about linear functions, let me do a real quick example here. So linear functions, you have 0, 1, 2, 3, right, so we have 5, let's do 8, let's do 11, and let's do 14. So this is a linear function because when you look at the rate of change, basically just the differences in the output here, we should always have the same number. Right, so 8 minus 5 is 3, 11 minus 8 is 3, 14 minus 11 is 3. That makes this thing, this data, if you want, linear. Whereas quadratic data, or quadratic function, when you're modeling it, it has a linear rate of change. So when you take the differences here, they don't look all the same. But there's certainly a pattern. There's a linear pattern. Right? So we say they have linear rate of change. And then you can actually even guess for a cubic function. If you have a cubic function and you want to know what it is, right? A linear function has constant rate of change. A quadratic function has linear rate of change. A cubic function will have quadratic rate of change. So when you look at a table of a cubic function, so let's do one that's really simple. Let's do 0, 1, 2, 3, and let's do 4. And so here, if you look at the first one, it's, how am I going to do that? But 0, 1, 8, 27, 64, and maybe I need to do one more. So let's do one more, 5, and then 125. When you look at the distance on these, the differences on this data, which is cubic, by the way, I just cubed these to get these outputs, you'll see that this is 1, this is 7, this is 19, this one is 44 down 7, so 37. And then this one is what? Go down 60 to 65, go down 4 more to 61. And so you'll notice that the first rates of change, they're certainly not linear, but if you look at the next rate of change here, so next rate of change here, this is 6, this is 12, this one should be 18, and then this one should be 24. Okay, and then if you look at the rates change one more time, you'll see there's actually a clear pattern. That's 6, that's 6, and that's 6. And so you see it doesn't have a linear rate of change. Here's a linear rate of change right there. It actually has a quadratic rate of change. And you can just build what we call polynomial functions in this way. So a cubic function is quadratic rate of change. A quadratic function over here has linear rate of change, and a linear function has constant rate of change, and so on and so forth. Okay, so let's take a look. Let's talk a little bit more about this stuff. So we answered this question. What is a quadratic function? Something that has linear rate of change. We talked a little bit about the tables. Let's talk a little bit about graphs. So graphs and quadratic functions, there's basically two types of graphs. It's just sort of like with lines, right? Lines go up or they go down depending on whether the slope is positive or the slope is negative. Same thing really for sort of quadratic functions. You can have a quadratic function that opens up, looks sort of like a U up, and it has this vertex right here, which we label h comma k. And we call this the vertex. It's basically the lowest point on this graph. But besides opening up, you could also open down. So you could also open down. Let's put it over here for fun. And here's the vertex right here. And still we label it h comma k. And there are also actually two formulas for quadratic functions, two types of formulas. You can use what's called the vertex form, or we can use the standard formula. We're going to focus mostly on the vertex form because it's kind of nice. You can see here's the formula, y equals a times x minus h y squared plus k. I don't typically have you memorize this formula, but you should know h comma k is the vertex. What's nice about it is a kind of determines whether you open up or down. When a is positive, the quadratic function will open up. When a is negative, it'll open down. So it's kind of nice. There's a nice connection kind of with slope if you think about it. When m is positive, the line goes up. Right? So if m is bigger than 0, the line goes up. When m is negative, the line goes down. And of course, h comma k here is the vertex. The standard formula is something you're probably most used to, y equals ax squared plus bx plus c, and it's nice. It's nice for the quadratic formula if you're solving an equation, but this one's really nice for interpretation, and we'll come back to it in a little bit. But let's first take a look at an example. All right, so here's an example with sort of focusing on quadratic graphs, and we want to kind of review some of the old things we did with these new types of functions, like finding the domain. So remember, the domain or input values. Remember, these arrows mean go all the way down, and then of course all the way to the left, and this means go all the way down, of course, to the right. So if you think about it, all these input values here have a graph above or below it. So domain is everything. So d here is equal to minus infinity to infinity. Whereas the range is not going to be everything. It's going to be a little bit limited. It's limited by what? So if you go and look at the graph, you'll notice that it goes all the way down. So the range goes all the way down to negative infinity, but it only goes up to this height 3 here. And even though you don't draw a closed circle right here, it's assumed that it is included. If it wasn't, you'd have to put an open circle. So I would say you go from negative infinity all the way to the bottom, all the way up to 3, and make sure you include 3 because that's the highest point. It's the highest output value. All right, so now what we want to do is we want to find the maximum value. Okay, of course, that's not too hard to do. So the maximum value occurs right here. Now you just have to remember that the maximum value isn't the input, it's actually the output. So the output is 3, so the maximum value would be 3. But if you want, you can give it to me in functional notation, say f of 1 is equal to 3. That way you don't make any mistakes. If you just put down 1, it's actually not right, because by definition the maximum value is the output, not the input. Find the coordinates of the vertex. Well, we actually already have done that. So this is 1, 3. And so if you plug in 1, right, you get out 3. So there's the vertex. And finally, we can find this formula here. We found the vertex to be 1, 3. So that tells us that h is 1 and k should be equal to 3. And so what we have now is this formula, f of x equal to, now we don't know what a is, so you have to copy down a, but we know what h is, so we can write x minus 1, quantity squared, and then we know what k is, plus 3. And to find a, let's give us some room here. So to find a, we'll erase some of this stuff on the picture so you can see it. You're going to need another point. So which point are we going to choose? Something nice. So I like to use usually the y-intercept if it's nice. So this one looks nice. So the y-intercept, if you plug in 0, you get out 2. And so that's a piece of information. I can use that to figure out a. So when you plug in 0, that means x is 0. So we have a left parenthesis 0 minus 1 quantity squared plus 3. And the output, which is the f of x part, is 2. And so now we can go ahead and solve this equation, and that'll give us an answer for a. So 2 is equal to, maybe square negative 1 to get back 1, so you just have a plus 3. And then we take away 3 from both sides, and we wind up with a being equal to negative 1. So now we can write down the formula as f of x equals negative x minus 1 quantity squared. And you can put negative 1 there for a if you want, but negative's fine. And you add 3 to it. Right, and that's my answer. So this is my answer in vertex form if you want, using the vertex formula. You could also multiply it out if you wanted to. If you multiplied this out, you could rewrite this in the standard form. Right, so remember the standard form is ax squared plus bx plus c. But if you really wanted to, you could multiply it out and you get negative x squared minus 2x plus 1, all plus 3. And of course that would be equal to negative x squared plus 2x. And then a minus 1 plus 3 would be a plus 2. And so you can do that if you want. You can write like this in standard form. Right, so this would be the standard formula, using the standard formula if you want. So standard form, or using the standard formula. Right there, or this is using the vertex formula. Of course, the answer is fine just like this. It really doesn't matter to me. All right, let's move on. Let's talk about something else now. So we talked about the graphs here. I want to focus a little bit more on the formulas and kind of where they come from. So if you think about this formula, you can think about this in terms of transformations on y equals x squared. And then it makes it obvious why h comma k is actually the vertex. So if you take this graph like this, and you subtract h4 from it, what that is actually it's a horizontal shift, right, in the direction of h. Now h could be positive or negative, but let's just assume, so this is minus, so I'm going to say to the left, let's assume it's to the right. So what that does is when you do x minus h, it takes you right here to h. So that's x minus h, x minus h quantity squared. Let's do it like this. So x minus h quantity squared. Now when you multiply by a, that's on the outside, so remember it's like a vertical stretch, or it could be actually a vertical shrink. It can be positive or negative, so you can reflect over the x-axis if you want to, so you can turn it upside down and stuff like that. But when you add k to it, it's just going to shift it up. So if you want to think about it, it could, a can make it sort of more narrow or wider, but when you add k to it, when you multiply by a, that's what it does. But when you add k, it's going to shift it up. So if you add k to this, right, maybe a is going to make it a little bit more narrow, but adding k just shifts it up. So h comma k. So whatever a is, it'll do different things, but this would be the formula y equals a x minus h quantity squared plus k. So it's sort of an easy byproduct of applying transformation simply to the graph of x squared. And of course the standard formula comes from multiplying all this stuff out like we did in the last problem. You get this ax squared plus bx plus c. So let's do another problem here, and we're going to go back and forth. We went from the vertex formula in the last problem. I showed you you could go from the vertex form to the standard form just by multiplying out. Now we're going to go the other way. Okay, so standard form. So now I want to go the other way. Basically, I'm going to give you the standard form, and I want to see if you can't rewrite it back in vertex form, which is nice because then it tells you the vertex. And once you know the vertex of the quadratic function or parabola, then all you need to know is if it opens up or down, and you can pretty much graph it. All right, so we're going to use completing the square to do this. We're going to use completing the square to rewrite the formula in vertex form. So this is actually pretty simple once you master it. It takes a little bit of work, but it's not too bad. So let's just copy down the formula. F of x equals, and we have x squared plus 6x plus 10. And remember, to complete the square, we just memorize this little saying. We want to add half the middle term squared. And if you just write this down every time you do it, you'll have no problem memorizing it. It's half the middle term squared. And so if you look at this one, we have x squared, and then plus squared there, and then plus a 6x. And so 6 is the middle term. You can take half of it and square it. So half of 6 is 3, squared is 9. And remember, take it off right next to it. So plus 9 minus 9. And then you still have this plus 10 on the end. And now what does that do for us? So remember, when you do complete a square, what happens is this thing right here turns out to be a complete square. Hence the name, completing the square. So if we rewrite this thing, it's going to be x plus 3 quantity squared. Right, that's what this thing in red is. And then minus 9 plus 10, that's just a plus 1. And so now we can actually read off the vertex here. So remember the formula, which again, you don't have to memorize, but it helps to know if I'll give it to you, but it's nice to know. So f of x equal to some number a times, left parenthesis, x minus h, quantity squared, plus k. And so from this, we can read off our h and k. Now be careful because h is a little bit tricky. It's not positive 3. The vertex is actually negative 3. And the reason for that is because it's minus h. And here you have plus. So there's really a minus if you want. So that's why h is negative 3. And of course the k is just 1 because it's plus k, so plus 1. So there's a vertex at negative 3, positive 1. So here's my vertex right here. And then to graph this, I know it opens up, but you probably want to get one more point. And so the easiest point typically to get for a function in general is if you plug in 0. So you plug in 0 to this formula, this will be 0, this will be 0, and you're just going to get out the number 10. And so it must go through 10. And then we simply connect these dots the best we can, which can sometimes be difficult, but just try the best you can. Connect the dots, and if you can't, just trace over them a couple times to make it look smooth. And then, of course, it should look basically exactly the same on the other side, although sometimes it's hard to do. But it looks something like that, basically, where the vertex is right down here at negative 3, comma 1. And it passes through this point 0, comma 10. All right, let's do another one, but let's make it a little bit harder. So let's look at this one. And first, let's make sure we know why it's a little bit harder. So it looks kind of similar to the one we did before, but the difference is you have this 3. And that 3 makes all the difference when working this problem. So let's come down here. We want to use completing a square to rewrite the formula in vertex form. We can rip off the vertex. But here, let's copy it down. So 3x squared plus 6x plus 10. Now we want to add half the middle term squared so we can complete a square, but it's not going to work on this problem. And again, the reason why it's not going to work is because the coefficient, or if you want to say the leading coefficient, is not 1. It's actually 3. So somehow we have to get rid of that 3. So the way we do it is actually pretty simple. Pretty simple idea. We don't like it. We want to get rid of it. So we factor it out. So factor out a 3. And we're going to factor out just to here. And we can factor 3 just out of there. And so what we have left over is an x squared. And you have a plus sign. And then you have to turn this 6x. What happens when you factor out a 3? You get a 2x, right? Because 3 times 2x is 6x. Then you have this plus 10 on the end. So these are exactly the same thing. You just factored a 3 out of the first two terms. But now what happens is you can complete the square of this inside expression. So again, let's write down the saying. We add half the middle term squared. Alright, so let's do that. So what's the middle term in this expression? Well, certainly it's not 3 here. Certainly it's not the x squared. It's the plus 2x, right? So the middle term is the 2. Half of 2 is 1. When you square it, it's 1. And remember, take it off right next to it, in parentheses. So we're right here, and then on the very end you have plus 10. And again, why do we do this? The reason we do this is because this thing right here should be a complete square. So we can rewrite this as 3 times, and then we'll write this as x plus 1, quantity squared, with a minus 1, in parentheses, and a plus 10. And so then finally we can multiply through by this 3 here, and get what? We can get this to be 3 times x plus 1, quantity squared. So just distribute 3 through, so it goes there and it goes there, and then minus a 3 plus a 10. And then of course we can combine like terms, so that minus 3 and plus 10 can combine to give us 3 times x plus 1, quantity squared, and then plus 7. And again, we can read the vertex off of this. It's not too hard to do. And remember the form, if you like. F of x is equal to a times x minus h, quantity squared plus k. And we just look for, the proper position. So the a is 3. We don't really need that. Remember the vertex is h comma k. So if you want, we can just write h comma k. And what would that be equal to? Well, you may want to put 1. But you have to be careful. Remember, it's minus h. So it's not positive 1. It's negative 1. And it says plus k. So plus 7. So now my vertex is at negative 1, 7. So here's negative 1. Go up to 7. Let's put a little dot. We can even label it if you like. So it's really clear. It's negative 1 comma 7. And we need one more point when we graph it. So easiest point to graph always is just plug in 0. So if you plug in 0 to this function, notice what happens. The first 2 terms are 0 and you just get back 10 again. Great. So it passes through 0, 10. So you can put a point there. You can label it if you want. And then we just connect the dots. So here's my dot connection. Goes through there. And basically does the same on the other side. Oops, that was terrible. So basically it's supposed to do the same thing on the other side. Right? Doesn't have to be perfect, but if you put the points on there, then it's good enough. Okay, so what's next? We talked about what a quadratic function is. It has linear rate of change. We talked about, looked at a table example. We looked at tables with graphs, talked about the vertex, talked about the 2 types of formulas. There's the vertex formula and the standard formula. They do the same thing. And remember, this is similar to when you work with linear functions and you have the slope-intercept formula, or you have the slope-point formula. They do the same thing. Right, but they're nice to have. This is really nice for interpretation when you're looking for the vertex. This is kind of nice to have if you're working when you're trying to when you're sort of solving equations or something. And then we move on to modeling. So modeling is, of course, one of my favorite topics. It's my favorite because you get to create your own formula from a picture, basically, and use that formula to do something. So remember, my 4 steps for solving any problem in the world, or a word problem in a math class, is first we want to draw a picture. So here we have a farmer decides to enclose a rectangular garden with 600 feet of fence using the side of a barn as one of the sides of the garden. Find the maximum area of the garden. So here you have a rectangular garden, so let's make our garden here. You have a barn for one of the sides, so let's say we have a barn on this side. Of course, we'll label the horizontal stuff X, vertical stuff Y. I probably wouldn't label this Y because you don't need a fence here. This is a barn. I have 600 feet of fence. Notice that's not area stuff because it's not feet squared. This is the amount of material I have. And always write down what you need to find. I find that that's one of the most important things to do because we often forget what we're trying to find. So we want to find the max area. These are called optimization problems, and the idea is you find a formula for something, and then we can use a piece of technology, in our case our graphing calculator, to optimize it, to find the very largest or smallest, which we call the max or min. And so for our equation, it depends on what we're trying to find. So we're trying to find the max area, so I'm going to look for an area equation, try to maximize it, or optimize it if you like. So that's x times y, length times width. Of course, I can't graph that because I have x and y, so I need to get rid of one of these, and that's where this number is going to come in. So this number here, 600 feet, is the amount of fence I have. So I can write down 600. I can express it, basically, in terms of x's and y's. So you have 1x, 2x, and 1y. So 2 x's plus a y. Remember, x and y stand for x feet and y feet. So you have x feet plus y feet plus x feet should be equal to 600 feet. You can solve this for y by taking away 2x from both sides. And so what do we have? We have 600 minus 2x is equal to y. And then the idea is we can take this y and replace it with what it's equal to. 600 minus 2x. So a will be equal to x times 600 minus 2x. And now this is a formula that we can graph. And it's a quadratic formula because when you multiply through by the x, you get 600x minus 2x squared. So it's clearly quadratic. But all we need to do is take out our calculator here to solve the problem. So here's our calculator. We want to basically graph this function, so turn it on, hit y equals, and then we're just going to graph it. So you have x, and you have left parenthesis, and 600 minus 2x in parenthesis. And in order to graph it, we need to set up our window. We have to know where to look. So you have to think a little bit. You have to think about what x represents. So x represents the length of this fence. So you can start at 0 for no length. And then you can go up. Now I wouldn't go up to 10 because you have 600 feet of fence. So I might go up to about half of it, or you can kind of just guess and check. But if you do 300, you'll see you get a really nice picture because it's half of 600 and there's 2 x's basically. But you can really just guess and check. And so then we're going to go to zoom and find zoom fit. So I usually scroll down and find zoom fit or 0 and hit enter. Then we're going to get a nice looking graph. Oops. We're going to get a nice looking graph that goes up and comes down. So the input is the length, right, of this fence here. And then remember the output actually isn't y. Remember, it's the area. That's important. All right, so let's copy this graph down to show some work. So now I'm solving, basically. I'm solving this problem. I graphed this between 0 and 300. I remember from the picture, my calculator went up and came down. And so I'm trying to find the maximum right here. And what you'll notice on your calculator, if you hit second and then the trace button, which takes us to the calculate menu, you'll see there's actually a maximum button. So you can hit maximum, and then you can just scroll to the left when you think you're to the left of the maximum and hit enter, and scroll to the right, and you can watch it kind of pass the maximum there. And when you feel comfortable, that's the right, hit enter. Then you just hit enter for a guess, and it'll jump right to it. And so on this one, we want to find the maximum area. So you have two choices. You have this x is 150 and y is 45,000. Now remember, this y and this y are not the same y. This is the length of the fence here, whereas this y is our output, which remember is area. So all I really care about is that number there, the max area, is 45,000, and of course it's feet squared. I'm just ripping that off my calculator there. It says 45,000. So this point right here, that point was 150, comma 45,000. And I want the max area, so I want the 45,000. And make sure you put feet squared because the units matters. If you put feet, it's wrong because it's not area. It has to be feet squared. There's no real way to test this problem, although you can go back and you can actually find the dimensions if you want. If you know x is 150, so if we know x is 150, then you could probably figure out y, because y is 600 minus 2 times x, so it's actually 300. If you take 300 times 150, you get 45,000. So, maybe it's right, but it's hard to check this problem. Actually, in calculus, you learn a way to do it without technology, and we often use our technology to actually check if our answer is right. All Right. Then the next, so that was a geometric problem. The next type of problem is sort of a table problem. And I enjoy table problems too because you can really see the formula and how formulas actually work. So on this one you have an airline carries 6,000 passengers per month, paying $200, and a market survey indicates for each dollar decrease in ticket price, the airline will gain 50 passengers. Determine the ticket price that will maximize the airline's monthly revenue. So maximize revenue. All right, so I like to highlight or underline things, and then I trim down and try to draw a picture. And so my picture usually involves a plane, because I'm like, this is a plane, so here's my plane. I have 6,000 passengers, so I'm going to just draw some people here. And so 6,000 people. Right, so you write people if you want, or just leave it. It doesn't matter as long as you know what it is. And then over here, I have paying $200 each. So each paying $200 to fly in that plane. So $200 each. It's hard to write on this tablet. So $200 each. And then what? And then it says, the survey says for a $1 decrease in tickets, so if you go down $1, something happens basically, right? So we take $1 and we go down. What does this imply? Right, this implies that we'll gain 50 people, so we'll go up by 50 happy people. Right? They're very happy. And we want to determine the ticket price that maximizes the airline's monthly revenue. So find, let's write down what we need to find because that's usually the most important thing. It tells us what the next step is usually. Find price max revenue. That's enough for me. You might want to write more if you want, but that's all I need. So find price max revenue. So my equation, what I need to find a revenue equation, and then I'm going to search for that price. So I'm going to make a little table basically, because I know some things, and I have an input value and an output value. So I'm going to let X be the number of $1 decreases. And there are all kinds of ways of this. So X is defined to be the number of these things, $1 decreases. So when X is 0, you're going to get out some revenue, R. And so if you have 0 $1 decreases, what you know is you have 6,000 people, each paying $200. So over here you can write 6,000 if you want, times 200. And that's your revenue. Okay, 6,000 people and $200 per people. When you multiply it, you'll get dollars back. I don't really care what the actual value is, but I need to find the form because I want to find the formula basically. And then if I can find the formula, I can graph it and find that maximum. And then that should lead to the ticket price I need to charge. So let's now pretend like X is 1. So what does that mean? You made $1 decrease. And so what happens to the 6,000? So 6,000 passengers becomes 6,050. Basically, you add 50. Then what happens to that 200? Well, you went down $1, so that 200 becomes 199, or 200 minus 1. You don't want to do the operations or the calculations because you'll lose the form, so it'll be hard to discover the formula. So now what happens with 2? Right, 2 what? So 2 $1 decreases. Well, you get the $50 from before, 50 people from before, plus another 50. So you have 6,000 plus 50 plus 50, or if you want, 50 times 2. And then over here, instead of going down just $1, you went down 2, so 200 minus 2. And you're going to start seeing a trend or a pattern occur. And once we see the pattern occurring, things become really obvious as to what the formula actually is. So let's do one more and then we'll basically have it. So what happens when you do 3 $1 decreases? Well, you have 6,000 to start with, and you go up 50, not once, not twice, but 3 times. So 50 times 3. Then you start with $200, but you did 3 $1 decreases, so you don't go down by 1 or 2, you go down by 3. And once you see the pattern, now you can do it for X. So what happens if you have X? $1 decreases. Well, clearly you start with 6,000. You add 50, and then you can see the pattern. Here you can put a 1, and so if you have 1, you have 1. If you have 2, you have 2. If you have 3, you have 3. If you have X, you just put in X there. And then let parentheses, and you have 200 minus. And so now what goes here? But you see, if you have a 1, you put a 1. If you have a 2, you put a 2. If you put 3, you put 3. If you have an x, you put an x. So your brain can identify that there's a form, and then you have to work with it a little bit to establish the formula. But now I know that the revenue function, r of x, is equal to 6,000 plus 50x in parentheses, and then all times 200 minus x. Now that is a quadratic function because when you multiply this out, you do get x squared stuff, although I'm not going to do it. It's not really part of the problem. The next thing I want to do is I want to create this sort of, I want to solve this, and I'm going to solve it with my technology. I'm going to solve it with my graphing calculator. So here's my graphing calculator. I'm simply going to graph this thing, so hit on, go up to y equals. Let's graph this quadratic function. So I have left parentheses 6,000 plus 50x, in parentheses, left parentheses, 200 minus x. Hit the window button, and here's where I have to think a little bit, alright? So for x, I'm going to start x at 0, because that's $0 increases, and I'm going to go up, I don't know, let's go up to 100. So we could increase by 100, or decrease by $100. And let's see what that looks like. So zoom, and go to zoom fit, that'll fit the output to the input. Let's see what it looks like. So it goes up, and it comes down. I'm looking for the maximum. Ah, look, that's actually perfect. Doesn't get any better than that. So let's copy that graph down. So it started up here, came down here. I went from 0 to 100. I'm looking for that maximum, so let's punch that in. Hit second, trace to pull up the calculate menu, number 4, or if you want, scroll down to maximum. And then you can do left bound and right bound, so you can just scroll over and just hold it usually. That's definitely to the left. It goes up, somewhere up there I'm hitting a maximum. I don't know where, but I'm to the right. Hit enter and then hit enter for a guess, and out pops my answer. So it looks like my answer is x is equal to 40, and then this is 1,280,000. So here we have 40, comma, 1,280,000. Looks like that was the answer I came up with. Alright, so now what? What do you do with this information? So now I know that the input is 40 and the output is 1,280,000. So remember, the input is the x stuff, and the output, even though it says y on here, remember it's not y, it's actually r. It's for the revenue. So I don't care about the revenue. What I want is I want to find the ticket price that leads to the maximum revenue. And you have to be a little bit careful because it's not 40. Remember what x is. The input is not the amount you paid for the ticket. It's actually the amount you went down on the original ticket. So the original ticket was $200, and you went down $41 decreases. So minus 40, which is $160, and that's my answer. So if you charge $160 in this case, you will get the maximum revenue of $1,280,000. Okay, and so I think we're done. All right, so we talked about all this stuff, quadratic functions, and what they are, the tables, graphs, formulas, and then we looked at some models.